In this video, we're going to talk about coordinate curves. So basically, coordinate curves are going to kind of be like latitude and longitude, but for any surface. So let S be a surface with parameterization R of st for S and t in some parameter domain D. The coordinate curves are obtained by holding one of the parameters constant. So we get two families of curves. In this first family of curve, we get a different curve for every fixed t naught. And in the second family, we get a curve for every fixed s naught. Okay, so let's find the parameter curves for the sphere above. So remember that the parameterization for the sphere is R of phi theta. It was a sphere of radius 2 centered at the origin. So this is 2 cosine theta sine phi 2 sine theta sine phi 2 cosine phi. Okay, so the parameter curves will just hold one of the parameters constant. So we'll hold theta constant first. And so what we have now are just going to be 2 cosine theta naught sine phi 2 sine theta naught sine phi 2 cosine phi. So what are these curves? Well, let's try to draw this as best as we can. So let's say this is the x-axis and this is the z-axis. Well, notice that theta is fixed at theta naught, but phi is allowed to vary from 0 down to pi. Okay, so what we get are lines or curves that look a lot like longitude lines, except it's just half of the longitude line. And if we want the other half of the longitude line, we would look at the curve R of phi comma theta naught plus pi. That'll give us the other side of the longitude line. Okay, so this would be one family of curves. So these are like longitude. And then another set would be where we hold phi constant. So R of phi 0 theta. What is this? This is 2 cosine theta sine phi 0, 2 sine theta sine phi 0, and then 2 cosine phi 0. Okay, so notice what's happening here. This is fixed, so this is fixed. This is a constant. Okay, and so now what we have, you can rewrite this kind of in the following way. This is going to be 2 cosine theta times some constant that I'm going to call a. The second component is 2 sine theta times another constant that I'll call a, or the same constant, sine phi, and then another constant b. So the height is b, it's fixed, it's 2 cosine phi naught. But now if we look at just the x and y components, this is a circle. This is the parameter of a circle of radius 2a at height b. So these are like latitude lines, or they are latitude lines actually. Okay, so coordinate curves on a sphere are going to be longitude lines if you hold theta constant, and they're going to be latitude lines if you hold phi constant. So let's look at this next example. Find the parameter curves for the paraboloid above. So we have two different parameterizations. So if you look at the Cartesian or rectangular, R of st is equal to s t s squared plus t squared. Now the parameter curves are going to be difficult to draw, so I'm not even going to try that, at least not now. So if we hold t constant, this is s comma t naught. This is equal to s t naught s squared plus t naught squared. Okay, so let's think about what's going on here. The x variable is changing, and of course that means the z variable is changing. So this is just going to be a parabola that's shifted up by t naught squared. Okay, so if you look kind of in the xz plane, you're going to get a parabola that's shifted up. And if you do something similar, if you look at r of s naught t, this is s naught t s naught squared plus t squared. Okay, so let's see if I can try to do this. So this is x, this is y, this is z. The paraboloid x squared plus y squared looks something like this. And I'll just draw part of it. Okay, and if we look at curves where the y value is fixed, we're going to look at curves that the coordinate curves are going to look something like this. So that would be like the first family of coordinate curves. And then if you look at coordinate curves where the x value is fixed, we'll have coordinate curves, parabolas going this way, and then this is now on the other side of the paraboloid, something like that. And then, okay, that's about as best as I can do. There's good pictures of this in Dr. Yaskin's book, so I would recommend that you look at it there. But now let's look and see what happens if we were trying to find the coordinate curves for cylindrical coordinates. So there we have r of theta s is equal to s cosine theta s sine theta s squared. And so now if we look at r of theta, let me silence my phone, r of theta s0, this would be s naught cosine theta s naught sine theta s0 squared. So now we have a circle of radius s naught centered at 0, but in the plane s naught squared. Then if we look at r of theta naught s, this would be now s cosine theta naught s sine theta naught s squared. So these are going to be, theta is going to be fixed, so these are going to be curves that just follow the paraboloid from the origin up. And again, let me see if I can try to draw this. So this is x, this is y, this is z. So a very bad sketch of the paraboloid would be something like this. And then if we say, if we hold s naught constant, so that means we're going to hold the height constant at s naught squared. And so what we're going to have is going to be a circle of radius s naught centered at the point 0, 0, s naught. So this would be like when s naught is fixed. Okay, and now if we were to look at a fixed theta, we would have a curve that follows the paraboloid up this way like that. So this would be for fixed theta, and then the green one would be for fixed s. And so these give these give coordinate curves. And so one of the things that we can do, let me draw a few more curves here. Might be pushing my luck. Okay, so these are some other coordinate curves for fixed theta. And let me draw some more fixed curves like this. Okay, so now this sort of gives a grid on the paraboloid. And so we can address this point by saying which green curve it's on and which orange curve it's on. So in other words, in terms of theta and s. And this is exactly what latitude and longitude does. You don't give, when you give your latitude and longitude, you're giving it in terms of the parameters theta and phi, though you don't really say it that way. That's what you're doing. You're not giving it in terms of some absolute position relative to the sun or the center of the earth or anything like that. It's based on latitude and longitude, which is based on the specific parameterization using spherical coordinates.